Welcome back. We're going to be looking at lambdas and types. I told you something last time that was kind of interesting, is that when defining a lambda, you're supposed to use auto. And there is a reason behind this. So let's take a look. First thing is every value in C++ must have a type. There is no option about this. So closures are not exceptions, and they must have a type. The thing is that what type is it? It really depends on how you define it. And that's kind of an annoying thing to say. It depends is not the kind of answer you would be expecting from me, but that's reality. That's how it is. So it could be simply a pointer to a function, and we've seen such types, right? Remember, if I write something like int parenthesis star foo parenthesis int a comma int b, then it basically means that foo is a pointer to a function that takes two ints and return an int, right? Using the spiral rule. We've seen that. So the type is well known. It's right there. It's looking at us. We can write these types very easily. But that's a plain pointer to a function, which means there are no states. There is nothing captured from the environment. So how do we capture things from the environment? What happens when you say instead something like bracket a comma b bracket int c, and then you say, oh, return a bool, for example, and then you define a body? What happens when you write an expression like this one? Well, the reality is that a and b are somehow appearing somewhere in the body of the function, and you want to capture them both. And since we didn't say anything, the default is by value. So how is that done? Well, the way it's done is quite straightforward. It's by actually defining a little package. I want to make a little box, and that little box will contain three things. It will contain a, which in this case I haven't specified, but let's pretend it's an int. Then it will contain b that happens to be an int. And then it will contain a third thing. And that third thing is essentially a pointer to a function that takes an int called c and spits out a Boolean. Now, how does this refer to that? Well, because embedded within this function, when the function has an extra argument, if you think about it, there is an argument which will be this block of memory. So this whole block of memory goes in as an extra argument alongside C, so that within this, when we refer to A, we really refer to the A field of the structure that's being received as an extra argument. And then everything is the same. So this gives us the internal representation. So then what is the closure? Well, the closure is none other than this box. So changing color again, this is my closure because it contains everything that's essential to me. So it's a struct. The way we define this is by having a struct. Then it's an anonymous struct, so it has a mystery name, and then it has an int that's A, an int that's B, and then it has the pointer to the function, so the pointer to the function, and I'm not going to try and write its type, that we refer to. So it could be that, or it could be this. Both things are perfectly defined closures. And remember that each time you define a closure, you're going to get a different struct, because you may be capturing something that's different. Actually, even if you capture the same thing, you're going to have different structure. Each time you capture, you get a structure. And therefore, you get a different type. Now, since it's difficult to write down this type, and it's quite counterintuitive for programmers to figure out, is this my type? Is this my type? We simplify the problem by saying, don't try to figure it out. Use auto, and the compiler will create a type, and it will infer that this is the type of your closure, and we'll run with it. There is nothing else to be done at that stage. So that's how this is going to work. Okay? So that's the basic mechanism. So a structure with the attributes and essentially a pointer to a function that implements the behavior of the body. Now, the way we're going to package that, you'll see it's in reality as objects, but that's exactly what's going on, right? We have this extra thing. It has an extra argument that's hidden, and that carries everything we care about. So it's much easier to use auto because you don't want to write down that type. Actually, you have no way of writing down that type because you don't know what the magic question mark is here. It's the compiler that produces it when he analyzes this line of code. So that's what we truly have, right? And it's a little bit puzzling that we're living in this kind of a special world, but that's exactly how things are happening, and that's what we need to remember. Now, that brings us a little bit of a problem, though, because if you recall, if I'm writing my find function, when I'm writing the find function, before I was writing the type of the argument as being something like this, because it took no argument. I've already shown you last time that I was making use of find, but I didn't revisit what the argument looked like for the closure. I showed you how we used the closure. I showed you the definition of the closure using the closure. I didn't show you the find implementation that actually needs to provide the type of its argument. And we just said, well, the type is really hard to know. We don't know if it's this or that. You should be relying on auto instead. And there lies the rub. We have a problem because C++ prevents you from using auto for the arguments of functions. Auto can only be for declarations of variable or the return value of functions, not for arguments. So how are we going to fix this, and how do we get out of it? Well, there is a solution, and that's a brand new concept in C++. It's part of the standard template library. That's this brand new type. So this is a C++ concept. It's this std function, which is templated by a type t, and that's meant to represent exactly this kind of an animal or that. It has the ability to represent both, and that's a clean type that's really reusable throughout by us whenever we want to manipulate that. So let's revisit now the find function and see how it's going to make use of that to specify the type of its argument, which ought to be something like a closure. Here it is. Again, it might be a little small, so I'm going to load it up in a buffer so that we can take a close look at this one. So let's just try and remember which buffer this is in. And I believe, oh, it's got to be find 6. Yes, it is, right? So this is almost what we want. Not quite. It's already a little more generic, so let's go back find 5 instead. Okay, so we don't quite have what we want, right? So, you know what? That's easy. Let's retype that. I will make a find 7 rather than looking for my file. Find 7.cpp, and let's do this. So I'm going to do what? First, I'm going to reuse most of the things that are the same. So here's my compare and the inclusion. Then I'm going to go steal down at the bottom my main function. Right? So here is my main function. Now we see that we have a vector of double. We're calling find. We're going to pass compare. No, of course, the whole point. There was no need for me to copy the compare function. I want to use my little trick of passing a closure. So I need to go with a capture list. Then my argument, double A, double B. And then I give my body. Okay. And what is the body? Well, it's exactly, I have the spec above. So I compute the absolute value of A minus B. If it's less than my epsilon, I'm going to hard code epsilon for now. I return 0 because they're close enough. If A is larger than B, I will return 1, else I will return -1, right? And that's it. I can get rid of compare. Now that I have this beautiful thing, I have this completely embedded within my main, right? So this is a clean main that's making use of that. And of course, this test, I don't need it, so let's get rid of it. So here I'm calling found it, and we have 5/3 again in there, and here the right value, and we're testing to an accuracy of 100. So this is perfectly fine. Now I just need to implement find, and we have it above us. So the definition we were working with is that my find is taking is a template. It's a generic function that takes the type. We're going to return a bool. We take a vector of t's as an argument. Let's call it x. We take a specific value t that we're looking for. And then there is this declaration that says, oh, the argument is a function. And now here we write the type like this. It's a function that returns an int and takes 2 double. And again, that's the type that goes into the template std function. And let's call it compare. Once that is done, then I can start implementing really my find function. And the code is up there, so I'm not going to bore you by reading what I'm doing, so you can follow me on the screen. If I can type, right? So that's it. I divide. I make the call. I put in C the result of my comparison between the element I pick up at the midpoint and the value that I'm looking. If that says yes, they are equal, then I return true. If it says that C is positive, then clearly I got to update up to be mid minus 1. Otherwise, I update low to be mid plus 1. And if I come out of the loop without success, then clearly it's not inside the container, so I return false. That's my find implementation, right? That's exactly what's on the screen above. So let's find 7. Let's see whether this works. Let's go to a shell. ls, so we should have find 7, yes, C++ find 7.cpp. Let's send that in find and use C++14 as a standard. It worked. I run find, and he says, yes, I found it. Okay, no big surprise, he found it. Let's try to make a test that will fail. So just 1.6 should do it. Compile, run, and now it doesn't find it. So this is working perfectly well. But even though it's working perfectly well, there is some ugliness that's ongoing in here, right? My find function is taking a template. And the template tells me the type of the values inside the vector. So it's a vector of t's, where t is any type. Remember what I said, I could use class or type name here. These two are equally fine, right? You do that, you recompile, well, it still works perfectly fine. So type name and class are really the one and the same thing. No restriction. So yes, you can say type name. Then I take a v that happens to be a reference to a constant t, while y a reference, a constant reference, I should say. Well, that's to avoid, if v is a complex thing, like a movie or whatnot, you don't want to copy it when you're calling the function. You want to have a reference to it, but you want to make sure you don't modify it accidentally, so it's a reference to a constant t. Okay, so that's perfectly fine. But then my function here returns an int and it takes 2 double. Wait a second, nothing about this talks about double. It talks about t's. So this is not as cute as it should be. I shouldn't be doing that. I should actually be reflecting exactly what's going on. My function takes 2 t's. That's what it takes. So compares takes 2 t's. Now at least I could pass not a function that takes a pair of double, but if I make find works with a collection of monkeys, then I can pass a monkey comparator that, or closure that compares monkeys, and everything should work perfectly fine. This is now much better implemented and far more reusable. So let's just check again. And here we're now getting into trouble. He's telling me a whole collection. Did I save again? Yeah, I saved. So he's telling me an awful lot of things that he doesn't like about me. In particular, he tells me, yeah, sure, you're calling find, but there is a problem. I cannot find any function that supports that call. Okay, well, I have implemented find, right? That one. So how come he doesn't find? So let's look at the next message. He says, blah, blah, blah. Candidate template ignore. Deduced conflicting times for parameter input operator. And then he gives us a complex template to say like, no, you're crazy, I don't like this. Okay, and he's talking about a different find. So this message, we can kind of understand. It's taking input iterators. Mine is not taking that at all. Well, I'm getting funny messages for a simple reason, is that there is a find that exists in the STL, and maybe he's trying to use that one. So maybe that's confusing and causing much more messages than what we care about. So let me remind it to my find so that there is no conflict. And here I will call my find. So now at least I'm getting rid of lots of messages that have nothing to do with me. And then I try again, and now I have only 2 errors. And the first one is the same as before. He's saying, like, sorry, I'm not finding the myFind implementation. But now the second message, he says, candidate template ignore could not match function int with these 2 type parameters against the thing that was passed in line 22 within the file. So now he's actually telling me there is something that's not quite right over here in terms of the type of the arguments we're expecting. He has trouble dealing with this. He cannot really match the type of these 2 together. That is the type of the closure I have here and the type of the arguments I'm manipulating in the function. Oops, sorry. He can't really do the type of the function that's up there. That's saying it's a function that takes a pair of t's and return an integer. These 2 things to him are not the same. He has trouble with that. Why is it? Well, it's a tricky question. It's really a limitation of the ways that C++ is doing type inference, which is something that he's doing. You notice that even though myFind is a templated function, I never actually explicitly instantiated the template, right? Here I'm just calling myFind directly and he figures it out. We'll revisit that. But then there is this big thing, and I told you what the type of that big thing was, right? The closure has this type. And somehow this type, he needs to match it with that type, and he gets confused with that. So that's what we need to actually try and clean up. And the way to do this is the following. Rather than passing it directly, I'm going to break it down in a smaller piece. So first, I'm going to take that out and move it like we did before and say auto compare equal, and I put my definition, right? And then here now, it tells me, well, I want to receive an std function. So I'm going to say, fine, let's be explicit. You want a function that is going to return an int and take 2 doubles. And how do I construct it? Well, I construct it from my CMP guy up there, right? And I should close my template. Okay, so that's now my correctly defined template. I'm saying, oh, I'm constructing a value that happens to be a function of the right type. Let's go back and try and compile, and this time I get no compilation error. So what did I do? I basically decompose first, creating the closure so that we get an object of that type, and then creating a second value of this type that happens to be an std function. If you want to be explicit, I can again take that line, pull it out, and say here I have an std function int double double, and that's the function f, let's say, and it's equal to compare, right? Or I could even say f and I pass it like that. Both forms are fine. And after I do this, then here I pass f, which is the guy I've just defined, right? Once I do this, again I compile, again he's happy. So this is a perfectly valid thing. So you tell me, okay, but that kind of defeats the purpose. Now my lambda is floating into thin space over here, and my call is 2 lines further down. Yes, true, but that's simply because I wanted to illustrate this decomposition. I can actually do both in one shot. I can take this entire expression that gives me the type, take out the f, put it here, and then I'm going to take my entire closure and I stick it in there. Now that I've done this, I should have, and I'm going to put that on a separate line so that it's a little more readable. I have the entire definition. Now I get rid of these two lines. Now the closure is back again at the place where it belongs. And if I switch back and compile, this still compiles perfectly fine, and it runs exactly the way we want it. It says false in this case, and if I re-increase, say, my argument to have more 6s, compile, run, and he finds it. So that's exactly what I want. Now everything is fitting together. I have a completely generic implementation of my find. I'm making explicit the creation of an argument to convert a value of that type into a value of this type so that it's fully usable. And what I pass inside the temporary value is my closure. And everybody's happy. It's working perfectly fine. So this works well, and we can actually do whatever we want. So that's what I wanted to cover on this segment. You've now seen that I'm making use of my lambdas together with the find function. I can mix and match templates and closures, and it works perfectly fine. And I can give a type to the argument of a function that's meant to receive a closure as an input so that I can manipulate it as anything perfectly happily. My only caveat is that when I'm actually capturing a closure, if I want to pass it, I need to do a little bit more work to be convenient when I'm dealing with templates. So that's what we've seen. Oh, sorry, I've been moving in my slides when I shouldn't. That's where we were. In this part, this is the find definition, which is kind of neat now. My find takes a function compare of that type, and everything is okay. Note that this is preserving runtime combination. Compare is still an argument to my find. It's not a template argument. It's an argument to the function. Note that last time we discussed that already. You could do a compile time composition by moving that argument directly into the template, and that will give you a slightly different flavor that gives you compile time efficiency because the function compare will be blended with my find at compile time. And there is, in this case, a little extra benefit is that we don't have to do the more complicated blending that you see here with creating a temporary value that can go away. So this is an exercise that we'll do in class when we reach this point, and you will practice a little bit on the composition so that you have a better sense of how we're mixing lambdas, templates, and normal functions to actually get the best of all those worlds. That's it for today, and I get back with you when we look at partials. See you next time.